1.5 part B. So we're going to start from example 6, which is finding a polynomial with the given zeros. So we start by analyzing the question. We have a degree, a polynomial of 4th degree. So we know that n is equal to 4. And because of that, we know that we could have at most 4 zeros. Now, some of those zeros are given to us, and we have 2 and negative 2, so that would be x equals 2, x equals negative 2. We also are told that we have an imaginary zero right here, and that would be x equals I. And because we know that imaginary zeros come in complex conjugates, then we must also have the zero x equals negative I. So from here, if we know all of the zeros, it is very easy for us to find the factors. And those will be x minus 2 times x plus 2 times x minus I times x plus I. So if we go back to the factorization theorem, linear factorization theorem, we can list all the factors coming from the zeros, like we see it's happening. Like you guys see them listed here, but we still need to find that a sub n, which is the leading coefficient. So that's in fact what we need this information for, to find the leading coefficient, which we refer to as a sub n. So far, based on the linear factorization theorem, our polynomial that we know is of 4th degree is the following: a sub n times the factors that we have found, and so from there we're going to use the given fact that f of 3 is equal to negative 150. So what that means is that if x is equal to 3, the y value is negative 150, or in other words, the f of 3 is equal to negative 150. So what it makes sense for us to do is that we turn this f of 3 into what the y value is, which is 150, negative 150. Then from here, a sub n will be our unknown, the one that we're looking for. And what I'm going to do is substitute every x that you see on the factors with the number given to us, which is 3. So that will be 3 minus 2, coming from here, 3 plus 2, coming from here, 3 plus I, coming from here, and finally, sorry, that should be 3 minus I, and this will be 3 plus I. Alright, so we're still looking for a sub n, so here 3 minus 2 is 1. 3 plus 2 is 5. And what we're going to do here with the two factors that look like, well, they are complex conjugates, and we multiply 3 minus I times 3 plus I, there is a shortcut that tells us that we take the real part and square it, and then, and we can do that because they're complex conjugates, and then we can take the coefficient of the I, which is a 1, and square it. And so that would turn into 9 plus 1, which is equal to 10. So then the number that we get from multiplying these two is 10. So now we have negative 150 on the left. A sub n is our variable, the one we're looking for. and we have the product of 1 times 5 times 10, that is 50. So 50 is multiplying a sub n, so to solve for a sub n, the leading coefficient, we divide negative 150 over 50. And so that will give us a sub n is equal to negative 30. So if I go back to this question, and I want to write the linear factorization for this polynomial, it will be the leading coefficient negative 30 times x minus 2, x plus 2, x minus I, and x plus I. Now, sometimes it is enough to leave the polynomial in factor form, and that will be enough. But if you have to distribute it, what I will suggest you do is that you take 2 factors at a time. And we know we're going to end up with a 4th-degree polynomial here. So the easiest thing to do is to group the 2 that contain real numbers and the 2 that contain, and the 2 that contain the imaginary numbers. So if I multiply that way, we'll get here x squared minus 4, difference of squares, and here I will get x squared plus 1. And then after that, I can multiply binomial times binomial. And that will give me x to the 4th power plus x squared minus 4x squared minus 4. From there, I still have to go ahead and distribute the negative 30 to every term inside. So that'll be negative 30 x to the 4th minus 30 x squared plus 120 x squared. Oh, actually, I can combine those like terms, right? Yeah. 1 minus 4. So that will be negative 30 x to the 4th plus 90 x squared minus 4. So that will be the polynomial if we expand it, and this will be in factor form. If I was to give you a test, a question like this on the test, I would be okay with you leaving it in factor form because it's very time consuming. So the next thing on 2.5 is the parts rule of sign. So this is named after the French mathematician, and he's the same guy who made the Cartesian plate because we didn't use it in elementary. So what it says is that the rule of signs, the parts rule of signs, it provides more specific information about the number of real zeros. So this is just going to tell you how many you may or you may not have, but it's not going to tell you what the zeros are. And so if you combine this one with the rational zero theorem, which you know tells you a lot of how many positives, how many negatives you have, the one that we had at the beginning. Oops, right here. So this one tells you, let's look at the one here. So for example, if we're using rational zero theorem combined with the part rule of signs, we could, and if we say there are only 2 positive ones, then maybe we could save some time by not testing the negative ones, because that rule of signs will tell us that. Or it could also tell us we only have 1 negative, so then there's no point with testing all the positive ones. So let's see how we're going to apply it. And so what we have to do is consider the variations in sign between consecutive integers. So consecutive coefficients. So two coefficients that are one after the other are consecutive. And so here we have a positive sign, here we have a negative sign. So from here to here, we're going to count one sign change. And then we stay with negative, negative, so no sign change. And then we went from negative to positive, so that will be two sign changes. And then we stay from positive to positive, so no sign change there. And then from positive to negative, so that will be another one. So in total, we had 3 sign changes. So what that means is that we could have 3 positive real zeros. Now, that is just a possibility. It's not just for sure that that's the case. Now, how can we find about the negative real zeros? So we will have to find f of negative x, which I know you guys love to do. And so you substitute every x with a negative x inside parentheses. And then I'm going to simplify it. So from the very first term here, negative x to the 7th power is equal to negative x to the 7th power. And so if I multiply that times 3, it will be negative 3x to the 7th power. Now from here, I'm going to get also, so I have negative 2 times negative x to the 5th power. So that would be negative 2 times negative x to the 5th power, and that will equal to positive 2x to the 5th power. So that will go here. The next term right here, we will get a positive x to the 4th. So because we have a negative here, that will still be negative x to the 4th. Next term here, we will get positive x squared, so plus 7x squared. And we have here negative x and minus 3. So now we're going to count the sign changes. And those will be from negative to positive. That we consider one sign change. Positive to negative, that's another one. Negative to positive, that's another one. And then positive to negative, that's another one. So we have a total of 4. So what does that tell us? That we had 4 sign changes when we try the f of negative x. And so therefore, we could have potentially 4 negative real zeros. And I want you to notice that the degree of this polynomial is of degree 7. And so that polynomial could have at most 7 zeros. Right? So if we were to add 4 negative zeros and 3 positive zeros, of course it does make sense, right? But not all the time you will use the exact number of sign changes, because we have another rule. And so that says that you consider the number of sign changes, which we already know how to do. And we have this or statement. It will be less than, so that means we're going to subtract less than the number of sign changes by a positive even integer. So the first positive even integer is 2. So the example we had at the beginning, we had 3 sign changes. So if we subtract 2, we get 1. So then what that tells me is that if I have 3 sign changes, I could have 3 positive zeros or 1 positive zero. So 3 positive zeros or 1 positive zero. Now, if we subtract another even integer, like such as subtract a 4, you will get here negative 1, and there's no way you can have negative 1 possibilities. So then we just say either 3 or 1. So for our negative case, we had a total of 4 sign changes. So based on this theorem, we could have either that, the number of sign changes, when we computed f of negative x was 4, or we can keep subtracting negative integers, we're subtracting even integers, so that would be 4, or 4 negative zeros, or 2 negative zeros, or if we subtract 2 minus 2, we get 0 negative zeros, which is like none. Now keep in mind that these are number of possibilities. It doesn't mean that x equals 4 is a 0 or x equals 2 is a 0. It just means that you can have 4 negatives or 2 negatives or 0 negatives. Alright, so we're going to do last example with it. So let's use this table first. So we count the sign changes from here to here, that's 1. And then from here to here, that's 2. From here to here, that's 3. So we have 3 sign changes. So in conclusion, we could have either 3 positive zeros, or if we subtract 2, it will be 1 positive zero. The one here, we counted 2 sign changes, so we could have 2 positive zeros, or 0, which means no positive zeros. Same thing here, we have 1 sign change, so 1 positive 0. And we can now subtract that 2, because if we have 1 minus 2, we will get negative 1, and we can now have a negative possibility. Okay, so let's do this problem last. So we have, you can see all the signs are positive. So here we have no sign changes for f of x. So therefore, there are no positive real zeros. To find the negative zeros possibilities, we have to first compute f of negative x, and so that will be negative x to the power 3 plus 2 negative x to the power 2 plus 5 times negative x. And we added 4, so that will give us negative x to the power 3 plus 2x squared minus 5x plus 4. And this is f of negative x. So now if we count the sign changes, we will get from here to here, that's 1. Here to here, that's 2. And here to here, that's 3. So what this tells me is that we could have 3 negative real zeros. Or if we subtract an even integer, such as 2, we could have 1 negative real zero. And since our polynomial is of degree 3, we know that we could have at most 3 zeros without counting multiplicity. So it's either we have 3 independent negative real zeros, or we might have the same negative real zero, perhaps it is repeating. Or maybe we have some other zeros that are not even real. So I'm just going to solve that. We don't have to based on the question, but I'm going to solve it. So if we have that polynomial and I use the rational zero theorem, I will take the factors of the constant term, which is 4. That will be plus minus 1, plus minus 2, and plus minus 4. The factors of my leading coefficient, which is 1, will just be plus minus 1. So then my possible rational zeros will be all these numbers divided by 1. So I will have positive 1, negative 1, positive 2, negative 2, positive 4, negative 4, and we have 6 possibilities. But out of those 6 possibilities, we already know that there are no positive real zeros. So I can cross out all those possibilities. And so if I want to test, I'm reducing my testing options to only 3. So I'm going to start with negative 1. And the coefficients for this one were 1, 2, 5, 4. So if we do that, negative 1 times 4 is negative 1, 2 minus 1 is 1, negative 1 times 1 is negative 1, 5 minus 1 is 4, negative 1 times 4 is negative 4, and that will go to 0. So that means we have found 1, x equals negative 1. Now, remember, you don't have to go back to the original coefficients. You just can keep going here once you have found 1, 0. So I can use negative 2. And that will be 1, negative 2, negative 1, positive 2, 8, and then negative 16. So that's not going to work. That is not a 0. So let's try our other possible negative number, which is negative 4. One, negative 4, negative 3, positive 12, 16, and then negative 52. So you can see that it's not going to work either. So what is this telling me? That we're not going to have 3 negative real zeros. We only have 1 negative real zero. So if they're not positive or negative or real, what else do we have? We have imaginary. And so we started here with something of degree 3, degree 2, degree 1, and the constant term. So after we divide it by a factor such as x plus 1, because the 0 is x equals negative 1, then we obtain the coefficients for the polynomial 1x squared plus 1x plus 4. And so x squared plus x plus 4 is non-factorable, so we have to rely on the quadratic formula for that one, where the coefficients will be a is equal to 1, b is equal to 1, and c is equal to 4. So if I use the quadratic formula, negative b plus minus the square root of b squared minus 4ac, everything over 2a, we're going to obtain negative 1 plus minus the square root of 1 squared minus 4 times 1 times 4. Everything divided by 2 times 1. So from here, negative 1 plus minus the square root of 1 minus 8, 16. Or 2. So negative 1 plus minus the square root of negative 15 over 2. to negative 1 plus minus I square root of 15 over 2. So that will be negative 1 over 2 plus minus square root of 15 over 2 I. And keep in mind that here we're getting 2 of them. So just to list all 3 of them, we had x equals negative 1, x equals negative 1/2 plus the square root of 15 over 2I. And the other one, of course, will be its complex conjugate because imaginary zeros always come in pairs. Okay, and so even though the question was not to find the zeros, I just did it so you can see all the terms apply in one single problem. So this is the end of the video. Thank you for watching. Don't forget to do your homework.